Welcome back, class. Thank you for joining me. Today we're going to move on to 5.2, talking about linear factors and zeros of polynomials. So in the first notes, we were talking about mainly vocabulary, how to describe these graphs. Well, now we are going to move on to talk about the zeros of these polynomials. So to begin, I'm going to start by looking at the factor theorem. So the expression x minus a is a factor of a polynomial if and only if the value a is a zero related to the polynomial function. Now when I say zero, there's a lot of different words you can use for that. You can be talking about the zero of the function, the solution of the function, the root of the function, the x-intercept of the function. All of those things mean the same thing. So what that means is every factor that you have for the polynomial in factored form produces a zero. Now, this is something you should be familiar with because we've already done this with quadratics. However, what I want you to see is it continues on when you're even talking about higher powered functions. So, zero product property is going to say this piece right here is going to give us a zero of -2. This piece right here is going to give us a zero of 1. This piece right here is going to give us a zero of 3. Okay, so basically it's breaking it down using the zero product property, setting each piece equal to 0 to find each of the solutions that you're looking for. So in this case, -2, 1, and 3. Now, don't forget, when you just have an x sitting out there by itself, you still set that equal to 0, and then you've actually already found it. When you have that x out front by itself, that just means x itself. 0 is a 0. Here, x plus 4 equals 0. So another solution is x equals -4. And then that one, when you set this equal to 0, now you have an additional step there, okay? You have to add the 3 over and then divide by 2. But each time you're getting a separate 0, a separate solution to your polynomial. Now, there are some cool things that can start happening when you're talking about these zeros. So when a linear factor appears more than one time in a polynomial, it makes a multiple zero. In general, a is a zero multiplicity n, means x minus a appears n times as a factor. All right, so let's take a look at what that mumbo jumbo means. So, looking at this, we're going to do the same thing. So, this right here, that x minus 1, is going to create a 0 at 1. Now, what I want you to notice, though, is notice that squared on that factor. Okay? That squared there is creating a multiplicity. Okay, it's saying that 1 is a 0 twice. So what we say is the 0 of 1 with multiplicity 2. Okay, because it's a 0 twice. It has that squared on it. What about this? So x plus 5 equals 0. So x equals -5. Now, that one, notice it does not have an exponent, so it doesn't really have a multiplicity. Or if you want to give it a multiplicity, with multiplicity 1. Okay? Otherwise, if there's no exponent there, it's a 0 just like we've always treated zeros. And then finally, what about that one? Well, that x plus 4, you said equal to 0, creates a solution at -4. But this one has a multiplicity of 3. It's a 0 3 times. So that's what we mean with these multiplicities, okay? It is acting as a multiple root. Now, let's do another example. So here, remember, when there is just an x sitting out front, that means you have a solution of 0. And what does that squared mean? Well, that squared means it's a solution with multiplicity of 2. That factor there creates a zero at -7. And notice it doesn't have any exponent there. So when you're asking for multiplicities, you can just say with multiplicity of 1. It's just a normal root. And finally, this one here. Again, this one takes 2 steps. Move the 5 over, and then divide by 2. And now notice the exponent on it. That 5 on that factor means it has multiplicity 5. Okay, so now we've gone over how to find the zeros. We've gone over multiplicities. Now I do want to show you something that I found very interesting from the book. Okay, so how multiple zeros affect a graph. So if a is a zero, multiplicity n in the polynomial function, then the behavior of the graph at the x-intercept a will be close to linear if n is 1, close to quadratic if n is 2, close to cubic if n is 3, so on and so forth. Okay, so what does that mean? Well, look at this right here. That 0 has a multiplicity of 2. Okay, it says that right there. So because of that, notice what happens. When your function is going up to it, it doesn't go through the 0. It touches it and goes back down like a quadratic does. So something that's really cool, really interesting is that those zeros with multiplicities, they take on the behavior of that type of degree of polynomial. So again, nothing that's going to be on a test for you, but something that's of interest, something just little fun fact for you about these multiplicities of how they're affecting these graphs and these functions. Now, the factor theorem also works the other way. So far, I've been giving you the factors. I've been asking you to make or to find the zeros for me. We can also do the reverse. I can give you the zeros and you can construct a polynomial. So let's look at our first example. Write a quadratic polynomial in standard form with zeros 3 and -1. All right, so thinking of these, so if I have a 0 at 3, let's think of what that would look like. Well, remember we're always getting the opposite behavior. So if my 0 is at 3, that means my factor has to be x minus 3. Okay, so that's something to take away from that factor theorem is whenever you're creating the factor, you're always getting the opposite sign of what you'd expect. Same thing that -1, well, doesn't that mean that came from x plus 1? Because you put in the -1 to get 0, you put in the 3 to get 0. So here's or an example of a function of degree 2 that has zeros at 3 and -1. Now notice, it says it wants it in standard form. Well, how do we get this in standard form? Well, we can FOIL this out. X times x is x squared. X times 1 is 1x. -3 times x is -3x. -3 times 1 is -3. Remember in the foiling process, then you can combine your like terms. So 1x minus 3x is a minus 2x minus 3. And there is your quadratic in standard form. So pretty basic, okay? Just constructing those separate factors and then foiling it out when you need to. All right, so write a cubic polynomial in standard form with zeros -2, 2, and 3. All right, so to get a 0 at -2, you're going to need x plus 2. To get a 0 at 2, you're going to need x minus 2. To get a 0 at 3, you're going to need that minus 3. All right, so for a cubic, we're going to have 3 factors. Now, this means to write it in standard form, we're going to have to FOIL/distribute twice. Okay, so I'm going to start by foiling out these first two. X times x is x squared. X times -2 is -2x. 2 times x is positive 2x. 2 times -2 is -4. Combine our like terms. Now notice -2x and 2x actually end up canceling off. So we're actually just left with this. Now, so we can bind the first two parentheses together. But now we still have to FOIL again. Okay, so for cubics, remember, you're going to have to FOIL/distribute through this twice. So x squared times x, and I'm going to move over here, is x cubed. X squared times -3 is a -3x squared. -4 times x is a -4x. -4 times -3 is a positive 12. And notice this time that there's no like terms to combine. We can actually just leave it right like that. All right, so thank you so much for joining me. Now, again, please make sure you have all of this written down, and so then you come back to class ready to work on our practice work.